Okay, so in this lecture we are going to discuss adjoint functors. Adjoint functors. So this belongs to a broad subject which is known as category theory, and this is a part of category theory. And my name is Dr. Muhammad Ismail Khan, and I am going to discuss adjoint functors here. But before understanding adjoint functors, we need to understand universal morphism. Universal morphism. Because without understanding universal morphism, it is very difficult to understand adjoint functor. So let me explain universal morphism before going into the discussion of adjoint functors. Once you grasp the concept of universal morphism, it really becomes easier to understand adjoint functors. So what is universal morphism? Let me say we are having two categories. One category is C. We represent this by C. So one category. And the other category is D. Second category. There will be objects in each of these categories. Let me say there is an object A over here, and there is also an object A prime over here. There can be many objects in the same category. So let me just consider these two objects, A and A prime. Similarly, there will be also objects in D category. So for example, we have X here. X is the object of D. Now there will be also morphisms between objects in these categories, and there is a functor between C and D. So let me take a functor F. F is a functor from C category to D category. So definitely this F will act on the objects of C, and it will give me some object in the category D. So let me say when F acts on the A object, I get FA. This is the object in D which I obtained from the application of functor on A. Now there will be a morphism from, definitely there are morphisms in each category between objects. So let me say the morphism from X to FA is U. U is the morphism. Now when will be this morphism a universal morphism? That is the question. So the question is, when will this morphism become a universal morphism? So let me define a universal morphism and then check it diagrammatically. So let F be a functor from C to D. We write this with black. Let F be a functor from C to D. A universal morphism is a pair is a pair A U, where U is morphism from X to FA. So it is actually this pair. You need to specify the object and also this morphism. So it is a pair which satisfies the following universal property. And what is this universal property? If there is a morphism from X any to any object FA prime, where A prime belongs to category C. So if there is a morphism from X to any object FA prime where A prime belongs to C, then there is a unique morphism H from A to A prime such that the following diagram commutes, the following diagram commutes. Okay, so verbally it becomes a little difficult to understand, so let me make it easier with the help of this diagram. So X is any object in D, X is any object in D category. If A is the object which we obtain after the application of functor F, and if A prime is some other object. Now, when is this morphism a universal morphism? Let me say this is the morphism, this is U morphism from X to FA, and there is some other morphism which also goes from X to FA prime, and let me call this G. We call this G. Now, when will be this U universal? So this U morphism is universal when there exists a morphism from A to A prime in C category. When we have here A and A prime and there is a morphism, dotted arrows means the existence of this is required. So let me say this is H. So then this we obtain here this morphism, we make it dotted, and this is FH, because the functor will act also on the morphisms. So when the functor F acts on H, so we get FH. So this is the situation. So now this U morphism is universal if this diagram commutes. So this is the condition which is required for U. But in the case of universal morphism, we also have to label the object and the morphism. So U is the morphism and A is the object here, with respect to which this morphism is universal. Universal properties appear again and again in mathematics in different places, and the meaning of this property is that that it has some universality. For example, if U is a universal morphism, so this means that for any other F, let me say FA prime, FA double prime, FA, we can have any other object on which when F acts, so then we can find such a morphism from FA to that FA prime or FA double prime, so that this diagram commutes. In other words, we can say that if I know that U is a universal morphism, let me say this U is a universal morphism, so then let me say if there is some other object FA double prime, so and there is some morphism from here, let me say there is some morphism, let me call this F, small f. So I can, instead of coming this way, I can find a morphism here which will be here, and that will be, let me say if A is here, then A double prime is here, so there will be a morphism here, and let me call this H1. So what will come here? F of H1. So there is universality in this morphism. Anytime you have a morphism from this object X, you will go to another, you can take a path to that object via this object. Instead of going straight to that object, you can find, you can go through this way. So that is the beauty of this universal morphism, that you have always this option, and this is unique. Remember, this thing is unique. F of H is unique. So that is the beauty of universal morphism, that whenever you have some morphism directly from X to any other object which is brought from category C with the help of functor F, then you can go through this, you can factor that morphism through this path, and this G will become G will be equal to FH after U, okay, which means this morphism, if you come through this way, is same as coming from here to here and then here. So you can always factor this morphism with the help of these two morphisms. So this becomes universal, that you can do this factorization for any other morphism. Okay, in category theory, you know that we can take the dual of a category. And what happens in the dual category? That all the arrows are reversed in the objects. So we can take the dual of this, and that will be also, and what will be its dual. So in the case of dual, if we have, let me say, x here and f a is here and f a prime is here. So in the dual concepts, all these arrows will be reversed. All the arrows in this diagram will be reversed. So what will happen in dual? The arrow u will be now from this functor to here x, and you know this u is universal morphism, and the arrow g will become from here to here, this will become g, so now the universal morphism from fa, now for the case of universal morphism, there must exist this arrow, and this will be and we require here that from a to a prime this arrow must exist. H is here. So again the concept is same. Now this u should be so let me see if all the arrows, okay, there is a mistake. I have to reverse this arrow also. So this will become like this. All these arrows will be reversed. So this is also reversed, and this arrow needs to be reversed also, because I am forming the dual. So now what will happen, that g will become, this will become u after fh, u composed with fh. So this diagram should commute. So here also the universal morphism means that you can always factor a morphism going into x from f into u and h, u and f of h. So this is the theme of the universal morphism. Universal property is always telling something that a property holds then for every object. So that property is evident over here, that if you have any, let me say if you have any fa double prime, some other object of category C, a double prime, and there is a map, we say f from here to here, then it is sure that there must be a map which is from fa prime to fa, and for that this will become f, let me say the map from A double prime to A is H1. So what will come here? F of H1. So this is the concept of universal morphism. Now what we will do is that we will apply the concept of universal morphism to adjoint functors. But before going into adjoint functor, let me take an example of this universal property. Now those students who understand abstract algebra and tensors, they will be able to understand this example. Let me say we have a vector space V, and let us represent the tensor algebra on vector space V to be represented by TV. So V is the vector space and TV is the tensor algebra which is generated on this vector space. Now we can always do this, that if we have, let me say, vector space here and there is tensor algebra on this vector space TV, and let me say there is some other algebra, let me call this A, capital A. Now definitely this vector space will be a part of this tensor algebra, so I can include this in this tensor algebra, or I can say that there is a mapping and I call this inclusion. I means inclusion. I stands for inclusion. So I can include this vector space in this tensor algebra. Now let us say that there is some linear map from this vector space to this algebra A. Let me call this G. So then the universal property says that there must exist a map from this tensor algebra to this algebra A. So this map must exist, and let me call this H, such that this G is equal to H after I. So this algebraic homomorphism must exist. So this is a universal property. If you have any other algebra also, let me say you have some other algebra which is, let me say, A2, and there is some other map from this vector space, linear map, to here, and let me call this G2. So then there must exist a map from this tensor algebra to this algebra, and let me call this H2, such that this G2 is equal to H2 after inclusion. So this is what is meant by universal morphism, and this is an example of universal morphism. So what is the universal morphism here? Actually it is the pair I and vector space V. This pair is actually the universal morphism, or you can for simplicity also write the vector space first and I later on. And what is I? This is the inclusion from vector space into the tensor algebra of this vector space. Okay, so after this we go into the adjoint functor. Okay, this example which we have done actually requires some understanding of abstract algebra, tensor algebra. So if you haven't understood this, it doesn't matter, and you can go next to the topic of adjoint functors. Hopefully you can understand that even without understanding this example. So let us go to the concept of adjoint functor. Adjoint functors. Okay, let me say we have two categories, C and D. We say this category is C and this is D category. There is a functor from F D to C. Let me call this F. And there is also another functor from C to D, and let me call this G. So those two functors are there. Now let me say there is object X belonging to C and there is object Y belonging to D. Now when this G acts on X, so I will have Gx here, and when this F acts back on G, so I will get F G X. So this will be the situation. I applied G on X, and then I again applied F on this G of X, so I obtained FGX. So now let me explain when there will be left adjoint functor. So a functor this is for left adjoint functor. A functor F from D to C is left adjoint functor to G if there is, if and only if, there is a universal morphism from, and what will be this universal morphism? If there is a universal morphism, and you know that I write it in brackets, that a universal morphism is actually a pair, and let me specify the object X here, and let me write epsilon X, and this is actually what? This is from f of gx to x, and not x here but g of x. So if there exists a universal morphism from f to x, so then this functor is actually left adjoint functor. And you know that what is meant by a universal morphism. If there is a universal morphism which is from f of gx to x. So let me write this in diagrammatically. So what is the meaning of this? We have already explained universal morphism, so I want to see when this functor will be f will be a left adjoint functor. Okay. So let me say I have this object x over here, and I have this f of gx, or I can also make it in this manner. Okay, it is all right. F of gx, and also I can have fy, because f can act on this and bring it here. F can act on it and it will become f of y. So I can have fy. So the morphism from f of gx to x, we represent this with epsilon x. So this morphism is universal, which means that if there is a mapping from any other f to x, let me say g is here, then there must exist a map between y and g of x in D category. Here it actually this is inside D category, as you can see here. So there must be a map from y to g of x let me call this H. Let me label it with different color so that it is okay. So this is from y to gx, so when the functor f acts on this map, it will come here, and this h will become f of h. And this diagram will commute, which means g will become equal to after f of h. So this is just universal morphism, but wait a minute, this property should hold for each object x of C. So I should write it here. If there is a universal morphism for each object x belonging to, for each object of C. So this universal morphism exists for each object of C, which means if I take a second x, let me say there is a second object x prime. So, again I should hold this equation, should hold x prime. There is, let me say f of y is here, here. So, if this is a universal morphism, now this will become epsilon x prime, and then this is some morphism, let me call this small f. So, then this will exist, and that is f of, let me say h prime, can use any notation where this diagram will commute. So, this is what we call left adjoint. Remember, in left adjoint the universal morphism is from f to x. So, you must remember this point because it is very helpful in distinguishing it from a right adjoint functor. So, what is right adjoint functor? Right adjoint functor. So, let me define it. So, this is the definition. Let G be a functor from C to D G be a functor. Then G is right adjoint functor of F if there is a universal morphism so let me write it in brackets. In this universal morphism is actually, let me represent this with eta y, and this one is fy. Fy is the object, eta y is the morphism, and this eta y is the morphism from G after fy universal morphism for each object of y. So, this each object of y, this is necessary for each object y. Let me remove this, belonging to D. So, this should hold for each object. This property should hold, universal morphism property should hold for each object of D. So, you can understand this from here, from this diagram, that when we bring this y over here, so it becomes f of y. This becomes f of y over here. And when I again apply g on this, so this will become g of f of y. And the universal morphism should be, okay, let me complete this. I haven't written this here, that how should this universal morphism be. So let me write it. It should be like this. Eta y should be from y to g of f of y, and this should hold for each object y belongs to D. Okay, so universal morphism should be from this y to this, should be eta y. So diagrammatically I can write it like this. Let me say there is y over here, and then there is g of f of y, and here this is g of x So now if there is a map universal morphism from here to here, this is called eta y. So then if there is a, so this must be universal, okay, and this universality is on f of y. This universality is actually on this y. So if there is any other map, let me say g from y to g of x, then there must exist a map between x and fy, and this will be in category C. X and fy, this is an inside category C. You know that x belongs to C, so there must be a map from this to this. We call this H. So it will come here. This will become G of H. And this diagram must commute with me, which means that G here will become equal to eta y or G of H composed with eta y. So this morphism eta y must exist for each object of y in category D. So if this is true, then we say that G is the right adjoint functor. So that is a basic requirement. So now we come towards an example of this left and right adjoint functors. So what is the example? I think with the help of example we can clarify these concepts quite easily. So now I will take an example of this. Okay. For taking this example, we take pre-order sets. Pre-order. You know that pre-order is a set with a binary relation, and this relation is actually which type of relation? Which is reflexive, which has these two properties. Reflective means A is equal to A, let me say like this, and the other property that this must have is transitivity, and this, or we can say that the set must be transitive. So the pre-order relation is transitive, and this means that, let me say, if A is less than B and B is less than C, so this implies that A is less than C. So these two properties hold actually in pre-orders. So what is an example of a pre-order? An example of a pre-order is this: the set of integers with this relation. This is an example. For example, if you take this category, you can consider it as category in which the objects, we say this is the category, and which category? Category of integers with this pre-order relation. So definitely it has elements, let me say -1, 0, 1, 2, 3, 4, 5, etc. And there are morphisms. The relation is this: the morphism in these categories are less than relation, is this less than or equal to relation. So we see that -1 is less than 0. It satisfies this property. 0 is less than 1, 1 is less than 2, 2 is less than 3, this is less than. So there is a morphism from -1 to 0, that is this morphism, and then there is a morphism from 0 to 1, which is this. So these morphisms actually exist between these elements, and you can compose these morphisms, which is a requirement of category. In category, the morphisms must be composable. Also there is morphism, this one, from 1 to 1, and what is this morphism? This is equal to, less than or equal to. So this relation holds. Similarly, for 4 we have this relation, less than or equal to 4, because 4 is equal to 4, so this becomes a category. And similarly, in the same manner, we can form category of the real odd numbers, where the pre-order relation is less than or equal to. And in this category, definitely there will be real numbers. For example, 0 can be there, 0.1, 1, 1.5, 6.5, and this relation also exists here. We say this relation holds. So there are morphisms from 0 to 0.1, 0.1 to 1, 1 to 1.5, and similarly. So now these are two different categories, and we want to set functors between them. So how can we do this? Okay. So one category is over here. Let me redraw this. The second category is over here. This one is integers category, and this one is the real numbers category. Now, in integers categories there will be integer numbers 1, 2, 3, 5, etc. And in the real category there will be real numbers. So I can make a functor from this category z to here, and let me call this functor inclusion functor. I stands for inclusion, which is from integers to real numbers. And I have another functor which is from real numbers to this integers, and let me call this flooring functor. I is the, what is I? Inclusion functor, and this is actually the flooring functor. Okay, so what will this functor do? Definitely functor will act on the objects and morphisms. So the inclusion functor I will act on integer, let me say n, and it will include it in this real category. Let me say if I is 5, so it will give me 5. If I is 7, so it will give me 7. 7 is already available into the real category. So it will just include the elements of z into the elements of real numbers. And similarly, inclusion, when it acts on this relation, pre-order relation, so it will again give me this pre-order relation. So that is the inclusion functor. What is the flooring functor? The flooring functor will reduce the real number to the smaller number. Let me say 1.5 will go to 1, 2.1 2.1 after flooring will become 2, and similarly minus 1.5 after flooring will become minus 2. So this is the function of the flooring functor. Okay, now how these are related with adjoint functor? So we will show that the flooring functor is left adjoint to the inclusion functor. You can verify this by yourself very easily, because if you take any integer from this category, so there will be a universal morphism to the flooring category, to the flooring functor. So let me say, if you take 2 here, if you have some object, let me say 4 here, so I of 4 will come here, and for example, there is, in this category there will be numbers. I of 4 will be 4, and there will be 3.5, there will be 2, etc. So there is morphism, which means 2 is less than 4, and similarly there will be also 5, and which means 5 is less than 4 is less than 5. So you must remember that in the case of left adjoint functor, the functor is from f to x. So I can take this relation that 4 is less than 5, and this will become, there is a morphism from 4 to 5 in this manner, which means 4 is less than 5. Or you can say, let me say 5.1, which will be also here. So also there is a morphism, 4 is less than 5.1. So let me say, if I take this 4 and I apply inclusion, and after inclusion I4 I apply the ceiling functor again, this functor. So what will I get? Ceiling of I of 4, which means I of 4 is 4, so this will become equal to flooring of I of 4, so this will become 4. So there is a morphism from 4 to 4. We know that there is a morphism from here to here. 4 is less than 4, so there is a morphism. 4 is less than or equal to 4. This holds because 4 is equal to 4 actually. And now if there is any other morphism, if there is any other object which is brought by this flooring functor, let me say 5.1, so when I apply flooring functor on this, it will come here, and floor of 5.1 is actually 5, and we know that there is a morphism between 5 and 4, and that morphism is that 4 is less than 5. So it becomes in this manner, 4 is less than 5, and the arrow will go in the opposite direction to this symbol. For easiness, if this symbol is the arrow symbol and this symbol are always in the opposite direction. So now this means that there must exist a morphism between 4 and 5. Here, and that exists. 4 is less than 5, and when I apply this flooring functor on this morphism, so you know that let me write it here, floor of less than is less than or equal to, less than or equal to, floor of less than or equal to is equal to less than or equal to. So actually there is a morphism between these two, because 4 is less than 5, and let me invert the symbols. Four is less than or equal to 5. Okay, now there is a problem with this, and definitely this problem is very helpful in understanding our next part of this example, that you can see that this does not hold, the triangle does not commute. I cannot make such arrow. So what is the reason behind this? So actually I should have taken a number which is smaller than 4. For example, I can take 3.5. So if I take 3.5, so then what will happen? Let me take this 3.5. Okay, so this was a mistake, but this mistake is useful in the coming scenario, and you can see that it does not hold every time. If I have 3.5, so this will become 3, and then I will write this relation in this manner. So this will become, let me omit all these, this is also omitted, this is also omitted, and let me also omit this one. So now what will happen? 3 is less than 4, so what will happen here? I will have this, and it means the morphism is in this manner. So now I have this, 3 is again less than this 4, so I have this, which means the morphism is in this manner. So now you can see that this diagram commutes. This diagram commutes. If I go this way, I can go this way, or I can go this way, I will end up at the same place. So this means that this flooring functor and inclusion, flooring functor is actually the left adjoint of inclusion functor. Flooring functor is actually the left adjoint of the inclusion functor. So that is okay. So what was the problem with this number? Let me highlight this. What is the problem with this one? If you remember, the adjoint functor, the left adjoint functor, which we explained over here, this is the left adjoint functor. So the functor is actually from this object y to g of x. Okay, so you must remember that the functor is from y to g of x, while in this case we considered a functor In this case, we consider a functor which is from gx to I, and that was the problem. While in the case of 3.5, there is a functor, there is a morphism like this. Take this one. (3.5) is less than 4, so the functor is in this manner. So that was the mistake. That was the reason that this diagram was not commuting. But if you take the right objects for which there exists a relation here, morphism here, in this diagram must commute. And this happens for every object of this category, Z category, and this category. And therefore we can say that this flooring functor is actually the left adjoint functor of the inclusion mapping. Now the ceiling functor. What is the ceiling functor? Sorry. Okay, the ceiling functor will round up a real number to the bigger number, 2. 1.5. Okay, the symbols are inverted. Let me make the symbols in this manner. This is the symbol. So similarly, let me say 41.5 will be sealed to 42, and similarly ceiling of minus 1.5 will become minus 1. So now you can very easily verify that. So this is left as an exercise to verify. So this is exercise. You can take help in the comment section. You can check that the ceiling functor is the right adjoint functor to the inclusion functor. Okay, so this is enough, and we stop over here, and we will take further lectures also on the concept of adjoint functors, in which there we will consider more examples from more advanced topics like homotopy theory, and we will also check some properties of the adjoint functors. Okay, so hopefully this is enough for